Here we still talk about the single loop circuit. Okay, so actually it actually talks about the resistance in series or series resistance. Before we have already talked about series capacitor or parallel capacitor. Okay, so here we talk about the series resistance. So the circuit is somehow like this. We have a battery here, and then we have 1, 2, 3 resistor. Okay, so they are connecting back to back. Okay, so this node connecting to this node, this node connected to this node, this okay, so this is like back to back. Okay, 头接尾尾接头. Okay, so this is called a series 串联. Okay, so simply speaking, okay, I don't go through the derivation. Actually, it's quite simple. So the conclusion is that the resistance, the series resistance is nothing but R1 plus R2 plus R3. Okay, which means R equivalent equals to summation Rk, k from 1 to n, if we have a n resistor in series, n resistors in series, Okay, so we just add all of them together. Okay, so nothing special. Okay, so here there are two highlights. So it says when the potential difference V is applied across the resistance connect in series, the resistance have an identical current I, the sum of the potential difference. Okay, so the sum of the potential difference, which means the sum of the potential difference for this R1, this R2, this R3, and also this one. Okay, so we may somehow call this one is E. Okay, so maybe this one is a V. V1 is sufficient. Okay, V1, V2, and then V3. Okay, in this direction. Okay, so as I mentioned before, the current direction. Okay, it will be better to be from the plus side to the negative side. So we will have a V1 equals I times R1, V2 equals I times R2, V3 equals I times R3. So in simply speaking, we have E equals I times R1 plus I times R2 plus I times R3. Okay, so this is what the previous page, actually the derivation will be like this. Okay, so the second point is the resistance connected in series can be replaced with an equivalent resistance REQ, R equivalent, that has the same current I and the same total potential difference. V as the actual resistance. Okay, so which is like E equals I times REQ. Okay, so this one will be like R times R1 plus R2, R1 plus R2 plus R3. Okay, so comparing this one and this one, we will have REQ equals R1 plus R2 plus R3. Okay, so here if we have n resistor, we'll have a series resistance like this. Okay, so so here we have the potential difference. To find the potential difference between any 2 points in a circuit, start at one point and traverse the circuit to the other point, okay, for any path, and add algebraic the change in potential you encountered. Okay, so the point here is somehow like for example, if you like to find the potential difference VBA, okay, VBA defined to be VB minus VA, okay, VB minus VA. Usually we will just pick any point to be a ground node, okay, but even if you don't, this is still fine. But yeah, so here suppose we would like to find a VB minus VA denoted as VBA, so which means we start from this point and then we going this way. Okay, so we going this way. Okay, this E from negative terminal to positive terminal, so we will have plus E. Okay, plus E. Okay, 12 volt, and then actually we will know that the current of the circuit will be like clockwise. Okay, so here the I in this direction. So which means IR, okay, so we will have for this resistor, we have let's say it is VR to be, this is plus, this is minus. We will have a voltage drop if the current is going upward. So it will be like a minus I times small r, okay, I times small r, okay, this is small r 2 ohm, okay. So in that case, we will have E minus IR to be VBA, okay. So we just need to go through the element one by one to see whether the potential difference is added or subtracted. Okay, so here is like this, also V, okay, or maybe we can write it as a VBA to be E minus IR. Okay, so this point is grounding a circuit, just as what I mentioned. Grounding a circuit usually means connecting one point in the circuit to a conducting path to earth surface, actually to the electrical conducting moisture or rock beyond the ground, below ground. Okay, 就是界地嘛，界地，他讲了一个现实当中的界地，但是我们如果是电路的情况之下，界地的话的意思是就是零伏的意思，就是零伏的意思。就是如果你还记得24章很多题目的话，它就会假设说比如说无穷远是零伏，或者是某个地方某个导体某个面是零伏，它就是为了方便就是这里是零伏，那我就上下看这个是高多少伏，这个是低多少伏，就是电路层面就是这个感觉上比较简单，因为如果多一个数，就是你全部加一个数，虽然是一模一样的，但是如果有一个零的话，感觉上就会简单一些，就是等于说少一个变数的感觉少一个变数的感觉。Okay, so another point is the power of EMF device. So the rate P EMF at which the EMF device transfer energy to both to the charge area and to the internal thermal energy is P EMF is I times E. Okay, so I times E. Okay, so maybe sometimes I just write it as V. Okay, so it is also some sort of I times V. Okay, so for the element, let's say for the resistor, the power consumed by the resistor is still I times V or I square R or V square over R. Okay, so for a resistor, okay, the power consumption is P equals I times V equals I square R or equals V square over R. Okay, so all the three are equivalent for the resistor. Okay, so these two are specifically for the resistor, but I times V is generally correct for everything. Okay, even for this one. Okay, but for this one, this is the power provided by the battery. Okay, so maybe in the circuit, okay, we have one or even more battery. Okay, so you can calculate the power contributed then one by one, and then you can, or if this is just a resistive circuit, you can also calculate the power consumption by each of the resistor. Okay, so you add all of the power consumed by resistor to the total power consumption, and then you can also calculate the power generated by different battery. Okay, so this is the total battery generated by the power. So they should be correct if you compute correctly. Okay, so here's a sample problem. So here it says the EMF and resistance in the circuit in the following have figure A have this is figure A, so have a following values E1, E2, R1, R2, and capital R. So what is the current I in the circuit? Okay, so this circuit already have two battery. Okay, one. Okay, so actually it includes a real EMF. Okay, so with ideal source. Okay, so this is the ideal battery or ideal source, ideal EMF. Okay, whatever you can call it. Okay, so include an ideal EMF series with an internal resistor. Okay, usually this R1, R2 to be small. Okay, so in this case 2.3, 1.8, but the R is 5.5, or not necessarily not really small, okay. It is still in the same order. 就是通常的话，那种 R1、R2 那种内电阻的话，应该要比其他电路的元件的电阻值都要小很多，不然的话，很多的 power 都会在那边损耗。但是如果这个作为一个计算的题目的话，它就随便给一个数字，让它吃掉一部分的东西。OK。So here, what we need to concern at the first step is we need to determine the direction of the current. 第一步要看一下，因为这个 single loop 嘛，那电流要不然就顺时钟，要不然是逆时钟，那当然顺还是逆。Okay, so the first step is to see, okay, E1 and E2, they are connecting in opposite direction. Okay, so this is plus, this is minus, this is plus, this is minus. Okay, if we don't have the battery 2, if we only have battery 1, you will consider the current is clockwise. Okay, if we only have E2 without the E1, okay, then you will suppose the current will be counterclockwise. So they are conflicted to each other. Okay, so we need to determine which one is take the decision. Okay, so here we can see E1 is 4.4 volt and E2 is 2.1 volt. Okay, so E1 wins. So it turns out to be clockwise. Okay, turns out the I should be clockwise. Okay, so this is a single loop circuit. So let us maybe starting from this node. Okay, I can just call this one to be a ground node, and then we going clockwise. So the first one we try to go to this one, IR1. Okay, so going through R1. Okay, so it will be a voltage drop because the current is like this way. Okay, clockwise. So this should be a voltage drop. Okay, so we will consider a path like this. Okay, so the first one IR1 minus IR1. Okay, and then for the second one, okay, so for this node going to this node, this is a plus, this is minus. So this one should have a higher potential. So in that case, we should have plus E1. Okay, so this is done, and then we go to here. Okay, so this is plus, this is minus. So this is higher, this is lower. So from here to here, we should minus E2. And then from this node to here, okay, IR2 should be a minus. Then we go to point C, and then finally we have this capital R from here to here. So we should minus I capital R equals 0. Yeah, because we go back to VB again. Okay, so here we have equation with one unknown. The unknown is actually the I. So we just move let's say we just move this one to the other side. Okay, so we have a E1 minus E2 to be I times R1 plus R2 plus R. Okay, which can actually factor the common factor I. Okay, so finally we have I equals E1 minus E2, and then over R1 plus R2 plus R. So here we can just plug in every values. So 4.4 minus 2.1 all over 2.3 plus 2.3 plus 1.8 plus 5.5 to be 0.240A. Okay, so this is the current I. Okay, so for single loop circuit, this is extremely easy. Okay, so the second question is what is the potential difference between the terminal of battery 1? Battery 1 means VA minus VB, okay, VA minus VB, or VAB, VAB, okay, so we start from this node, going here and going here, okay. Up till now, we already done that I equals 0.2480, okay, from question A. Okay, so VAB will be like negative IR1 plus E1. Okay, starting from just repeat repeating like this, but we just stop up to here. Okay, because we just go from VB to VA. Okay, so we only include these two terms for this resistor and this battery. Okay, so this is like this, and it will be negative 0.240 times R1 is 2.3 plus 4.4, so this is nothing but 3.8 volt. Okay, so far any questions? Okay, so next we talk about the multi-loop circuit. So here it says that we have a junction rule. The sum of the current entering any junction must be equal to the sum of the current leaving that junction. So I always call it KCL. I don't remember junction rule at all. Okay, I always call it KCL, Kirchhoff current law. 这个不是氯化钾，不是那个potassium chloride 不是那个化学式子，这个是 Kirchhoff current law. Okay, so for multi-loop circuit, we usually can make use of the KCL to calculate to actually solve the circuit. Okay, so here is an example. We have two loops here. So yeah, you can consider this is a loop, this is a loop. And then in this circuit, we have a 1, 2 battery. We have a 1, 2, 3 resistor. 1, 2, 3 resistor. Okay, so yeah, if you don't familiar with the circuit, okay, and then you try to write quite a lot of let's say this is I1, this is I2, this is I3, and then you write a lot of V equals IR, and then you try to also apply quite a lot of KVL. Okay, maybe for this loop, for that loop, and then for the big loop, and then maybe tens of equations, and then you feel like you have 10 unknown with 10 equations, then you are not able to solve that. Yeah, especially sometimes you may make mistakes when you try to write a lot of equations. So in this case, yeah, I would say we will use something called a node analysis. In circuit theory, we will call it node analysis, although it is not included in the textbook. But yeah, just let you know, there is something called a node analysis, and in the next slide I will also tell you something about the mesh analysis. The node analysis, node means 节点这个是节点，中文叫节点分析法。Okay, so in that case, actually this one still applying KCL without using KVL at all. Okay, so it tells you that in a circuit you only need to either use KCL. Okay, so we call it node analysis. And next page I will call it I'll use the mesh analysis, which means I only use KVL all the way. Okay, Both are okay. Both are okay. Okay, but in this example, we only need one variable to use the node analysis to finish to solve this circuit. But if we use mesh analysis, we have two variables. Okay, so usually using node analysis, mesh analysis, the complexity of computation will be similar. Yeah, but for some specific case, yeah, choosing one will have less variable, then it makes your computation easier. 就是说，有这个节点分析法，有另外一个叫做 mesh analysis， 中文我也不知道这是什么。但是比如说我们用 node analysis 的话，它就告诉你说，哦，比如说这个电路我看到的话，就是我只需要一个变数，我就可以解这个电路。那 mesh 的话，哦，就需要两个。那但是大多数情况之下，两个方式其实可能计算复杂度差不多，很可能它们变量的数目一样，那你计算起来其实差不多难啊。那这个的话，如果只有一个变数的话，通常会比较简单啊。So let's see, okay, how I can say we have only one variable for this circuit. So first of all, we try to count how many nodes in this circuit. So actually, the figure already tells you we have 1, 2, 3, 4 nodes as A, B, C, D. Okay. So for the first step, I just picked this one to be a ground node for the node D. Okay. So this is already 0 volts. So we don't need to make it VA, VB, VC, VD, especially VD. Okay. Because we already know it is 0 volt. OK， 零伏的话，我就不要再编一个变数给它，因为你编一个变数给它，哦，它等于0就没有什么意义。OK， so out of the VD, okay, we still have VA, VB, VC. So the question is whether we need 3 variables or 2 variables or only 1 variables. The answer is we only need 1 because this is a battery. Okay, which means if we already know VB, if we already know what is VB, then VA must be VB plus E1. Okay, so we call VA and VB are dependent to each other. So 就是这个是线性代数的，就是说它们是所谓的相依，就是说它们是一起变的。就没有办法 VB 变一种方式 VA 变一种方式，它们就是被这个式子所束缚住，就是 VA 跟 VB 的差就是一个固定的 E1 啊。Okay, similarly for VC must be VB plus E2. So which means VC and VB are also dependent to each other. So which means VA, VB, VC.We only have single degree of freedom. 它只有一个自由度，就是 VB 怎么变 ，VA VB 就会跟着一起变啊，所以你不需要 VA VB VC 设三个变数啊，最终你还是写这两个式子出来。那当然你可以写3个未知数3个方程，就是多这2个方程，就是但这个就没有意义。So in this case, we determine that we only have this.variable. So we try to apply the KCL at this node. Okay, we try to apply KCL at this node. Okay, so for KCL, we try to compute the total current going in equals the total current going out. But in my habit, I always assume all the current is going out or all the current is going in. 就是你可以算流进电流的总和等于流出电流的总和，但是我的习惯是我会假设所有电流都流出或者所有电流都流进，因为它们这样加总的话等于0，这样你不会这样你的这种正负号其实会少一点机会算错的。OK， 比如说这里我们假设全部电流都是流出，你们就忽略这些 I1、I2、I3 啊，忽略这些。我们根本不需要用到这些我们假设所有的电流都是流出就好了。Okay, so in that case, for the first current from VB to VA, okay, we will have we will have VB minus VA. VA is actually VB plus E1, okay, and then over, okay, so what is the resistance? So the resistance, not like this, okay. I shouldn't write like this because this is not a resistor, okay. So actually this is what the student usually make mistake like this. Okay, so to determine the current, okay, we cannot consider this one. Okay, this is an ideal battery. The current of the ideal battery doesn't relate to the potential difference across it at any sense. Okay, the current can be arbitrary. So if we need to consider the battery here, actually we can consider the battery here. So which means, yeah, so this one is not correct. So for the current on this path should be like, we need to consider the resistor. So which is like VA. VA is actually VB plus E1 over R1. Okay, so this will be the current on this path, through this path. Okay, so this is the first current. And then for the second current in the middle, so it will be trivial VB over R3. Okay, so this VB, this is ground. Okay, VB minus 0 all over R3. Okay, so this is the second current. And the final current, okay, so we also ignore this battery, okay, and also ignore this one. Okay, we consider the current like this. So from this path, through this path. Okay, so this is like VC minus 0 over R2. Okay, so this is VB plus E2 over R2 to be 0. Okay, so these are the three currents, 1, 2, 3 current. The first current, the second current, and the third current going out from VB. Okay, so we add them up and then it should be equal to 0. Okay, so here we only have one variable, okay, VB. All the others are known values. So we try to collect the terms. So VB 1 over R1 plus 1 over R2 plus 1 over R3. And then we move negative E1 over R1 and then plus E2 over R2. Okay, so VB turns out to be a negative E1 over R1 plus E2 over R2, and then 1 over R1 plus 1 over R2 plus 1 over R3. And then we just need to plug in all the numbers in. Of course, in this example, we don't have any numbers. But so this is a general form, okay? So no matter what are the values for E1, E2, R1, R2, or R3, okay? So this is a general solution for the VB. So now, as much as you know VB, you can, let's say, for example, you just plug in the VB into here. So for the first term, it will be the current from VB to VA to the ground node. And then if you plug in VB to here, you may be able to calculate the current in the middle. And then if you plug in VB into here, you may be able to calculate the current from VB to VC to the ground node, something like that. So in that case, the node analysis tell you that, okay, first we need to count how many variables we needed. Okay, in this example, we only need one variable because VA, VB, VC are dependent to each other. So which means we only need VB. So based on we only need VB, we can just choose the node B, and then we apply the KCL there. So and then we have one variable with one unknown. Okay, so don't try to use VA and VC. Okay, because they are dependent to each other. Try to use VB plus E1 for the VA, and then try to use VB plus E2 for the VC. And then in that case, we only have a single equation with one unknown, and then we will be easy to solve VB out. And then solving VB out, and then we can know every single current or voltage difference across the circuit. Okay, so this is the first first method using the node analysis to solve this circuit. Okay, so far any questions? Okay, if no, okay, so still we have the same circuit, but here we try to apply the mesh analysis. Mesh analysis. Now, for mesh analysis, we try to apply the KVL. For node analysis, we try to apply the KCL. Okay, for the mesh analysis. Okay, for the mesh analysis, for this circuit, we can see still we try to ignore this I1, I2, I3. Okay, so they are just bothering us. Okay, so here we have a two small loop. So we try to define, this is I1, this is I2, this is I2. Okay, so based on I1 and I2, we will write two KVLs individually. Okay, yeah. So first is the first mesh. Okay, we'll call it the first mesh. Okay, so for the first, for the mesh 1, okay, so let's say this is also a ground node. Okay, so we start from here. Okay, here we will consider this is I1 from bottom to top. I1 from bottom to top. Okay, so I1 from bottom to top. So yeah, so this will be minus I1 R1. Okay, so I1 is from bottom to top, so this is the higher potential, this is the lower potential, so minus I1 R1, and then from A to B, okay, so the potential difference here, high, low, so this is nothing but negative E1. Yeah, because we just follow the direction of I1. Okay, so from here, this high, this is low, so minus I1 R1. Okay, this is high, this is low, so minus E1. And then from here to here. Okay, so this is a little bit tricky. Okay, for this R3, we have I1 from top to bottom, and then we have I2 from bottom to top. Okay, this is clockwise. So I2 for this, so it is somehow like we have I2 like this, we have I1 like this. Okay, so you can consider these two to be like from top to bottom, the I1 minus I2. Okay, like this. So in that case, we have a minus I1 minus I2, and then times R3. And then we go back to the original point, so it is equal to 0. So this is the first mesh equation. And then for the mesh 2, yeah, so we still start from the VD and then going here, going from bottom to top. So in that case, we can consider it is like from bottom to top, it is like I2 minus I1. So in that case, we have a minus I2 minus I1 and then times R3, yeah, for this R3. And then from here to here, low to high, okay, this is negative, this is positive. So we have plus E2. And then from here to here, we have a minus I2R2, like this. Okay, so here we have two unknown variables, I1, I2, I1, I2. Okay, all the others are known values. So in that case, we can try to collect the terms like I1 R1 plus R3 R1 plus R3, and then plus R3 I2 to be equal to negative E1. And then similarly, we can calculate, we can simplify the circuit like this is R3 I1, and then here we have a 2 R2, sorry, not 2 R2. This one should be R2 plus R3, and then times I2 equals E2. Okay, just some algebraic computation. Okay, we just collect the terms I1 to be here, I2 will be R2, R3 to be here, and then E2 here. Okay, so here we have a two joint equation with two unknowns, so we may be able to solve I1 and I2 to be something. Okay, and then in that case we may be able to know the current, and after we know the current we can know every voltage, so something similar to this. So if we know the voltage VB, we may be able to solve other voltage easily, or solve other, or even find every current easily. Here, if we already know I1 and I2, then we also can be able to find every single voltage easily. And these two are equivalent to each other. They should find the same answer. Even though for this example, using node analysis may be easier, but maybe for some circuits, using mesh analysis may be easier. Okay, so here we also talk about something called the resistance in parallel. So for the resistance in parallel, we have R1, R2, R3. Okay, so in that case, okay, so all the three nodes, they are sharing this E. Okay, we may be able to find I1, I2, I3. I1 to be E over R1, I2 equals E over R2, I3 equals E over R3, and then they add up to be the total current. Okay, so for the equivalent circuit, we just replace these three parallel resistors to be this Req. So similarly, I equals this E over Req, and then they are equal to each other, so that finally we will have this one. The reciprocal of Req equals the sum of the reciprocal of the resistance. Okay, or if we have n resistor in parallel, so we just take the reciprocal of all the resistance, add them together, okay, and then take the reciprocal again to get the equivalent resistance. Okay, so this is easy, and this is a quick summary for the resistance and capacitor. Okay, so they are opposite to each other. So for series resistance, we add all the resistance together, but for parallel capacitor, we add all the capacitance together. Okay, for the parallel resistance, we take the reciprocal first, and then sum again, and then add up all the reciprocal, and then take the reciprocal again to get the equivalent parallel resistance. For the series capacitance, we take the reciprocal for the capacitance, add them together, and then take the reciprocal again to get the series capacitance. Okay, so one more thing. How about the inductance? For the inductance, okay, if it is in series, okay, Leq will be summation of Li equals 1 to n. Okay, so inductance will be similar to the resistance. In terms of a series or parallel. Okay, so LEQ, 1 over LEQ. 1 over LEQ will be summation of 1 over this one should be J. Okay, this one should be J. Lj, and then J equals 1 to N. Okay, so in inductance is similar to resistance in terms of a series or parallel. Yeah. Okay, so here we have we have a quick sample problem. So let me finish it before the break. So here it says the figure A shows a multi-loop circuit containing 1 ideal battery and 4 resistance with the following values: R1, R2, E, R3, R4. What is the current through the battery? Okay, so it asks you the current here. Okay, it asks you the current here. So this is the current I, let's say. Okay, so first of all, we can see R2 and R3 are in parallel. So first of all, R2 parallel R3. So it will be R2, R3 over R2 plus R3. Okay, so it will be 20 times 30 over 20 plus 30. 600 over 50, which will be 12 ohm. Okay, so this is the parallel resistance. So after paralleling it, okay, so the equivalent circuit will be like, this is R1, this is R2 parallel. R2 parallel R3. Okay, and then R4. Like this. Okay, so this 1, 2, 3 resistance are in series. So which means the altogether the equivalent resistance will be R1 plus R2 parallel R3 plus R4. Okay, so this will be 20 plus 12 plus 8, so which will be 40 ohm. Okay, so which means I equals E over R equivalent. So it will be 12 over 40, which is 0.3A. 0.3A. Okay, so this is an equivalent circuit. And then if you need, it will be like this is REQ, okay, like this. Okay, so this current is the same as this current, and this current will be this one. Okay, so these two we still need to compute later on. So for question B, what is the current I2? What is the current I2 here? And then for C, what is the current I3 here? Okay, so so first of all, we would like to find VBC from here to here. Okay, so if you still remember, this is the equivalent circuit. This is a equivalent circuit. So these two resistors in parallel. So actually, this node is still VB. This node is still VC. Okay, so the VBC will be something like that. So VBC will be nothing but I times R2 parallel R3. VBC. Okay, so VBC. Okay, so this is I. And then going through R2, R3. So VBC will be I times R2 parallel R3. So which is nothing but, this is 12, this is 0.3, which is 3.6 volt. 3.6 volt. Okay, so in that case, I2 will be I2 will be VBC over R2. So it will be 3.6 over R2 is 20. Okay, so this is nothing but 0.18A. 0.188 A. And then what is the current for current I3 through R3? So I3 will be VBC over R3. So it will be 3.6 over 30. So this is nothing but 0.12A. So a quick note is that this is 0.3A like this. This is 0.18A and this is 0.12A. Okay, so we can quickly notice that 0.18 plus 0.12 is 0.3. Okay, so this somehow verify our calculation is okay.